The first thing we're going to review when reviewing concept 4, systems of equations, is how to solve a system of two equations with two variables, such as the one you see here, 2/3 x minus y equals 10 over 3, and 2x minus 3y equals 10. That's a system of two equations, each with two variables. So what we're going to need to do is first think about all the different methods we've learned in order to solve. If you actually kind of fast forward a little bit down to question 2 here, you'll see the three methods that we've talked about in class about how to solve a system of two equations. So to recap, to solve by substitution is usually useful when we have one variable by itself. So if we kind of look at what we've got, we can see that x and y not by themselves, x and y not by themselves in either equation. So substitution might not be the most efficient method here. We could try to get one variable by itself, but usually there's a more appropriate method somewhere else. Combination is another method that we've used, and combination is generally useful when all the terms are lined up, meaning the x's are aligned vertically, the y's are aligned vertically, and the numbers themselves are aligned vertically. Since we can see that in this particular sample problem, those vertical alignments appear to be present, it does appear that combination will actually be a good method for us. But just to recap the third method, graphing. Graphing is useful when both of the equations that you're given are in y equals mx plus b type form, where you can graph them and easily find their point of intersection from the graph. But since in this problem neither of these is given to us in y equals form, one of them doesn't really have the friendliest numbers to use, so graphing could be useful, but it seems like if we want to take advantage of the setup here, combination is going to be our best choice. When it asks us why we chose that method, we can simply say because the variables were lined up vertically and it was easy to cancel one of them. Now, before we actually go through and do that, we want to quickly take note of the fact that in this system, there are some fractions in one of the equations. That might be a little bit intimidating for some of us, so instead of worrying about the fractions too much, let's try to get rid of the fractions. The easiest way to do that is to take the entire equation, every single term, and multiply them by a single number. That single number, usually the denominator of the fraction that we're worrying about, should take care of everything in one fell swoop by multiplying and essentially doing the opposite of what that fraction is doing to us now. So since the denominator appears to be 3 in both fractions we want to get rid of, we're going to multiply every term in the equation by 3. If it helps you to think of it as 3 over 1, then you'll multiply by 3 over 1. It's kind of like the distributive property. You're going to multiply every term together. So in this first term, 3 times 2 is 6, divided by 3, which would be 2x. Then when we multiply 3 times negative y, that's minus 3y, equals, then we have 30 divided by 3, 10. So we multiplied, we took care of it, easy. Now we can copy the second equation, 2x minus 3y equals 10, and we realized something really familiar happened, that all of a sudden when we got rid of that fraction, we realized we got the same equation that we already had given to us in the second row. So technically speaking, if we want to follow this through all the way, we do want to solve by combination and try to make at least one of those variables cancel. The easiest way to try to make one of these vertical pairs cancel is to try to find a match. For instance, these two x's could match, but to make them actually cancel, we know we would need to multiply one of them by a negative, which essentially means that this becomes negative 2x, next term positive 3y, last term negative 10. When we do such a thing, 2x minus 2x cancels, leaving us 0. 3y minus 3y, 0. And negative 10, positive 10, 0. Which means every single term canceled out, leaving us with 0 plus 0 equals 0. Now that's a true statement. 0 plus 0 is equal to 0. And in this case, since everything canceled out, we say that this system has infinitely many solutions. So generally, we write that out, infinitely many solutions. You can abbreviate it as you wish. Just to remember, infinitely many solutions occurs when every single term cancels. The x's cancel, the y's cancel, and the numbers by themselves cancel. If you get the x's and y's to cancel, but the numbers don't, and you end up with a false statement, like 0 plus 0 equals -4, for example, that's when we would say this system has no solution. Now, fortunately, we don't have to worry about that here because we got 0 plus 0 equals 0, a true statement. But just in case you ever run into a false statement, you'll know that the solution to the system is none or no solution.